This is Ed Pegalon's independent design project for ECE 3873. I made a high voltage DC to DC converter. It takes in 36 volts from these four 9-volt batteries in the series, and it'll spit out here about 180 to 200 volts. It works by using a multiplier, which is just a configuration of capacitors and diodes like this. You can refer to the schematic for what that looks like. I'm using the supply to drive these three Nixie tubes that I imported from Ukraine. They're really cheap, pretty cool looking. Two of these on the right, these two on the right, they're just fixed on. Only one digit is on, and it's not changing or anything. It's just wired directly in. This one on the left, though, it's connected to this logic circuitry over here, which is, it looks like a mess, but it's basically just a 4-bit to 10-line decoder. I know like a 4-bit decoder would normally have 16 lines, but this one I made only have 10 because there's only 10 digits inside the tube, so those last six bits wouldn't even get used. The input are these switches here. You might be wondering whether there's 200 volts sitting on those switches. They wouldn't be safe to touch. No, there's only 9 volts on those switches. The only all of the high voltage circuitry is located on this breadboard here, and the only interface for the high voltage section to the low voltage section are these row of NPN switching transistors that I'm using to turn the segments on and off. So I'm going to go ahead and plug it in. Make sure I'm not touching something I'm not supposed to be. Now in my schematic I say that I'm using a 5-stage multiplier, but if you look, I'm only using 4-stage, and the reason why is I took one stage out because these tubes, they don't show it really in the video, but they're really bright. They're actually so bright that my camera wasn't doing too well with them, so I took one of the stages out to make them a little bit dimmer. But anyways, I've got this multimeter hooked up, and that's the supply voltage right now with those three tubes being illuminated, 160 volts. And to show how this decoder works, this is the binary input. So right now I'm not pushing any buttons, so it's 0 0 0 0. This one would be 1, this switch is 2, this switch represents 4, this represents 8. So for example, if I wanted to put a 9 in, I would hold down 8 and 1. That sums to 9, so it's showing a 9. And if I just push, for example, 2, then I get a 2. And I'll just run through all the numbers. And I'm going to show that not only do I get the digit for the combination that I'm pressing, but once I start putting in invalid inputs like 11, like there is no 11 digit, there's only 0 through 9, that the decoder doesn't do anything. Like it doesn't spit out bad cases or anything. So anyways, so here's 0, 1, 2, 3. Okay, it's kind of hard to push these. 4, 5, 6, 7, 8, 9, and then back to 0. Alright, I don't know how much detail I'm supposed to go into in this, so I'll just kind of give like an overview of the high voltage part. I think I pretty much covered the low voltage logic part. So I've got 36 volts sitting here from these batteries, and somehow I need to get like 200 volts out. So how am I going to do that? Well, I've got a 555 timer over here. It's only running on 9 volts. It's right there. Can't really see it that well, kind of dark. And it's oscillating at around 2 to 3 kilohertz. It doesn't really matter. It just needs to be in the kilohertz range to switch fast enough. And that is driving a totem pole inverter that has 36 volts from these 4 batteries on it. Now, it was really tricky to get this totem pole to switch right when you're only driving it with 9 volts, because you run into problems where the gates of the transistors aren't seeing voltages that are reasonable, and I've destroyed many transistors trying to figure out how to do this the right way. You can refer to the report because I go into a lot of detail on it there. Anyways, this 36 volts is getting switched at around 2 kilohertz, so it's a square wave. It goes 36 volts, 0 volts, 36 volts, 0 volts. And that's being fed into the input side of this voltage multiplier right here. The left-hand side is the input. This wire right here, this orange wire, is the 36 volt square wave. It's going into the voltage multiplier. This is called a Cockcroft-Walton multiplier. And the reason why I picked that voltage multiplier over a different topology of voltage multiplier is other topologies would require that if I'm putting 200 volts here on the output, then I need capacitors and diodes and things that are rated for 200 volts, but I don't have any on hand, and the lab doesn't have any on hand that are rated for more than like 50 volts, the capacitors anyways. So what this topology allows me to do is I only need components rated for the highest voltage seen on any of the stages, and since I'm switching 36 volts, the highest voltage I'd expect to see on any one of these stages is 36 volts. So I can get away with components that are only rated for 50 volts, over 36 volts anyways, even though I'm getting around 160 to 200 volts on the output. So that's why I went with that design. So yeah, that's pretty much it. The 36 volts goes in on this side, and every stage, like this diode here and this diode here, that's one stage. That diode and diode, that's another stage. So I've got 4 stages here, and that's getting the output that you see on the meter right here. And then I'm feeding that through these Nixie tubes. They're common anode, so they have 1 pin, and you put a resistor on the anode. I have 47K resistors. They're rated for about 2 milliamps a piece, so I'm only putting about 1.5 milliamps into them. And, yeah, that's it.